Hi everyone, this is Worksheet 8.1, Absorption, Stimulated Emission, and Spontaneous Emission. And in this video we're going to spend a little more time talking about the interaction between a quantum system that has energy levels and electromagnetic radiation. And in particular we're going to look at a little more detail about Einstein's theory of photons as well as Planck's explanation for black body radiation. So to begin with, let's consider the phenomenon of absorption. Now, in absorption, the system exists down at a lower energy level, and then here comes the photon. It comes in and it interacts with the system, and then the system will jump to a higher energy level. Now, the situation of stimulated emission is the case where the system is existing at a higher energy level and a photon actually comes in and hits it, and the effect that it has is that the system will drop to a lower energy level and it will release additional energy due to the incoming photon as well as the energy lost by the system jumping to a lower energy level. And then finally we have spontaneous emission, where just by random chance a system existing at a higher energy level will fall without interacting with any electromagnetic radiation at all, and when it falls to that lower energy level it will emit a photon. And recall that most spectroscopy is absorption spectroscopy. Now remember that Planck's constant times the frequency of light is going to be equal to Planck's constant times the speed of light divided by the wavelength. And this is equal to the absolute value of the difference in these energy levels. And another way to write this is Planck's constant times the speed of light times this nu tilde, where this nu tilde is 1 over the wavelength. And this nu tilde is also sometimes called the wave number. Okay, so in equilibrium, we're not always considering systems at equilibrium in this physical chemistry class, though in the other physical chemistry class, thermodynamics, we are considering systems at equilibrium often. But let's just assume that this system that we're considering is at equilibrium. In equilibrium, the number of systems transitioning to the higher state must equal the number transitioning to the lower state. So if the system is at equilibrium, it's at a relatively steady state, so there are equal numbers of transitions between the upper and lower state. And so here we've got another depiction of systems at different energy levels, and because of the Boltzmann distribution there are going to be more systems that occupy the lower levels and fewer systems that occupy the higher levels. And so let's say that there's a number n2 in the higher state and a number n1 in the lower state, like that. Now the system is, these systems are transitioning to these higher and lower energy levels. So let's think about the rates here. The rate is going to represent the probability that an atom, say, or you might think of it as a system, changes state. And this is going to be all over units of time. So really it represents the probability that an atom is going to change its state in a given unit of time. And the next three variables existed in Einstein's original paper, and this B12 rho nu represents an absorption rate, at a given frequency. So we can say at frequency nu. Okay, so this is the rate of transitioning between from state 1 ending at state 2 for a given frequency of light. Okay, now B21 is the stimulated emission rate at frequency nu. And this last number, A21, is going to be the spontaneous emission rate. Which doesn't depend on the frequency of light because it's not actually being, it's not interacting with any electromagnetic radiation except the photon that it happens to emit. Okay. So if those quantities represent the probabilities per time, imagine if we multiply it times the number of systems that exist at each of these levels, then we can actually get a total number of atoms leaving the upper state per unit time due to spontaneous emission. This number down here represents the total number of atoms joining the upper state per unit time. And then this final number is going to be the number of atoms leaving, again, the upper state per time due to stimulated emission. Now we're going to use these quantities on the next page. Okay, here we are on the next page. And if you recall, one of the things we said on the previous page was that at equilibrium, the numbers of transitions will be the same going between the energy levels, meaning an equal number of atoms will be transitioning up to the higher energy level, and as the number of atoms that are transitioning down to the lower energy level as well. And so what that implies is that N2 times A21, which remember is the number of particles that are transitioning from the higher level to the lower level due to spontaneous emission, plus the number of particles that are at the higher energy level times B21 rho nu. These are the numbers of systems transitioning due to emission, both spontaneous and stimulated emission, are going to equal the number of atoms that are transitioning due to absorption. So they're going to equal N1 B12 rho nu, like that. And this is the transitions due to absorption. Okay, so what can we do now? We can rearrange this algebraically a little bit. I can subtract this one here from both sides, and then I can pull out the rho nu. So I'm just going to do those two steps at the same time algebraically. So first I pull out the rho nu, and then I get N1 B12 minus N2 B21, and all of this equals N2 A21. And now I can divide both sides by this term right here, and I can get this rho nu on one side, and then the rest is N2A21 divided by N1 B12 minus N2 B21. Okay, so now if I want to get rid of the N2's, then I can multiply this whole thing by 1 over N2 divided by 1 over N2. Notice that's the same as just multiplying times 1, but it's going to make this expression a little bit nicer for us. So then we're just left with A21 on the top, and then in brackets we get N1 divided by N2 here, then B12 minus B21, like so. Now this spot right there has a ratio of numbers at the two energy levels, and that's nice because we can use the Boltzmann distribution for that. And the Boltzmann distribution says that if we compare the number of atoms at energy level A divided by the number of energy levels at level B, it just equals E raised to the power of the energy of the B level minus the energy of the A level divided by Boltzmann's constant times temperature. And since the difference between energy level 2 and energy level 1 in our system equals h nu, we can plug all of this combination of things in for right there. And this is what we get. The relative density of absorption or emission based on the frequency nu is going to be equal to A21 divided by B12 E raised to the h nu divided by kBt minus B21. Now if you compare this to Planck's black body radiation formula, then it looks very, very similar. We get 8 pi h nu to the third divided by c to the third times 1 over E h nu divided by kBt minus 1. Now, comparing these two directly, what that suggests is that not only does A21 over B12 equal this term out front here, so it equals 8 pi h nu to the third divided by c to the third, what's far more interesting is that B12 equals B21 at all frequencies. So that means that the rate of absorption is equal to the rate of stimulated emission. So that means that when a photon hits a system, it is equally likely to bump it up to a higher energy level or cause it to tumble to a lower energy level if it's already excited. And when Einstein first discovered this, it allowed for the development of lasers. This is how a laser works, which we will get to talk about more in class.